Welcome everyone. Today we'll be showing you a very friendly example of a multivariable limit that can be solved with polar coordinates. We're given a function of x and y that is defined for all real x and y besides the origin, and we want to find the limit as xy approaches the origin of this function. Let us get right into it. I'm going to start by writing down the definition of a limit and then explaining what it means. So suppose that this limit does have some finite real value, and we can call that value L. Then we know by the definition of a limit that for all epsilon greater than 0, there exists a delta greater than 0, such that if the distance between any point xy and where we're taking our limit to, the origin, if it is less than delta, then the distance between the value of a function at some point xy and the value of our limit L is less than epsilon. Let's unravel this definition. Basically, it says that for an input arbitrarily close to the origin, the corresponding output will be arbitrarily close to the limit, no matter how small epsilon and delta both are. And this definition is really useful for proving the validity of limits if we know the value of L. So for this question, we're going to make a very good guess as to what L is going to be, and then prove it using this definition. To make our guess, we can take this limit from a couple directions. Because remember, now in multivariable calculus, we take limits from an entire ball around some point, not just from two sides. I guess I would try the x-axis first. So the limit as x0 approaches the origin, which is literally just along the x-axis of this function, becomes the limit. So here the y terms just become 0, as is shown. So we have x cubed over x squared, which is just the limit of x with these bounds. And as x0 approaches 0, 0, in the limit of just x, that is, of course, 0. Okay, so along the x-axis, this limit becomes 0. I guess let's try the y-axis then. And for the y-axis, it will be a very similar story. Get the limit as 0y approaches 0, 0. So along the y-axis of this function is the limit. Now again, the x terms cancel out and we get 2y cubed over y squared, which is just the limit of 2y. As 0y approaches 0, 0, so y becomes 0. And this is just 0. All right, so from both axes, it seems to both approach 0. Can we find some counter example? Let's try moving along a line, for example, along the line y equals x. So the limit as x approaches 0, 0 of this function. So along a line, this becomes the limit as, so here we have x cubed, and we just replace y with x, so we get 2x cubed. And here we have x squared plus x squared. So this just becomes the limit of, looks like 3x cubed over 2x squared. So 3 halves x, yeah? And as x approaches 0, 3 halves x, that's also 0. Okay, so we've taken the limits from 3 different directions now, and we see that they're all equal to 0. So we can maybe conjecture that the overall limit, as any xy approaches 0, remember around the ball, is going to be 0. So if we put L as 0, maybe we'll find success in using the Epsilon-delta definition and proving that it is in fact so. Let's try that. Right now, our conjecture is that L equals to 0. So let's try to prove it. So as we start with an epsilon-delta proof, we suppose that epsilon is given and let epsilon be greater than 0. And our goal is to find a delta such that this holds true. So the distance between xy and the origin, which is just the distance of xy, if it is less than delta, then the distance between f of xy and L, which we conjecture to be 0, so literally just the absolute value of f of xy, is less than epsilon. We have to find such a delta in a general case, so expressed in terms of epsilon. Now, to find such a delta, here comes the clever part. We're going to use polar coordinates. So we're going to make a substitution where x is equal to r cosine of theta, and y is equal to r sine of theta. Just our good friends polar coordinates. Alright, so now we can express these magnitudes and this absolute value in terms of our new substitution. So the magnitude or the distance from xy to the origin in polar coordinates, well, come on, that's just by definition. We get that this magnitude is equal to r. Or if you're uncomfortable with that, it's just the square root of the x and y squared, x squared plus y squared. And squaring these up, Pythagorean identity, we get square root of r squared, which is r. And r is always positive. So that makes sense. And now I'll do this without absolute value for now, but I'll make some substitutions into our function. We get that f of x, y, which is equal to that. Well, let's substitute this in. We get r cubed times cosine cubed of theta, then plus 2r cubed, and then sine cubed of theta, over, and here we literally have r squared, right? Pythagorean identity to the rescue once again. So we can factor this out to get r cubed times cosine cubed of theta plus 2 sine cubed of theta over r squared. And this is equal to r times this entire angle in here, cosine cubed of theta plus 2 sine cubed of theta. Notice how through this polar substitution, we were able to relate the magnitude of xy and the function of xy through a single variable r. This is very nice, and it's a good sign that we are almost done with the proof. And we basically are. Now notice one more thing about this angle. By definition of sine and cosine, they are both no more than 1 in value, and doesn't make a difference how we're cubing them. So this cosine cubed of theta is no more than 1, and 2 sine cubed of theta is no more than 2. So their sum should be no more than 3. I don't know if this value is actually attainable, but it doesn't matter. We know that it's not possible for this to be more than 3. So we can say that this angle is less than or equal to 3. Therefore, the value of the function xy, and even better in absolute value bars, because r is always positive, know that this absolute value is no more than 3 times r. Now we are basically done with the epsilon-delta proof. Note that if this magnitude was less than r, then the absolute value of this function would have to be less than 3r, right? Because right now, if it's equal to r, this is no more than 3r. If this was less than r, this would also have to be less than 3r. All makes sense. So now we can choose a delta to be equal to epsilon over 3. And why? Well, if we have this, if we have the magnitude of x, y to be less than delta, if it is less than delta, then the absolute value of this function will have to be less than, you say it, 3 delta. And 3 delta is just epsilon with our choosing. And so we are done with the proof because we have found such a delta in a general case, such that when the distance from xy to the origin is less than delta, then the distance from f of xy to our limit is less than epsilon. So that is it for today's short epsilon delta proof video. Hope that helped anyone in need, and I will see you in the next one.